Hello everybody. In the last class we had a detailed look at three of the most important elements, that is the resistors, inductors and capacitors. We saw that energy flows from the source towards the destination, which is the load, and in between the energy can get dissipated in the resistor R, or it can get stored as kinetic energy in the component called L or the inductor. It can get stored as potential energy in the component called C, the capacitor, capacitance of the capacitor, or it can also get transformed from one type of energy to another type of energy, like electrical to magnetic, magnetic to mechanical, so on and so forth. In this session, we shall now focus our attention on this block, that is the source block. What are the electrical sources? What are the characteristics of electrical sources? What are the non-idealities? And have some look at real world and practical sources. If you look at electrical sources, the common ones that may come to your mind, one is the wall outlet. Every home will be having these 230 volt AC outlets, so you are all familiar with that one. That is one of the electrical sources, most common electrical source that you will be using. The second one, which you may have heard and probably also used, the batteries. Batteries are DC sources, very common, used in pen torches, used in laptops, used in many of the electrical equipments, your cell phones, so on and so forth. They are all batteries, DC sources. We will have a look at these also later. You have a third distinct type of source, the solar photovoltaic cell. These are slightly different in concept. We will come to it and have a look at it in more detail when we touch upon the solar cells. But they are becoming more and more popular in today's equipments, and most common one that you all would have seen is in the calculators, the solar calculators. There are also a few other sources like generators obtained from wind, hydro, so on and so forth, which are generated at the remote areas wherever there is a dam or wherever there is lot of wind in a particular location through windmills, and then connected to the grid and then routed to individual loads and homes. These are some of the more common electrical sources which you will be using in almost all of your electrical equipments. Now, if you look at the sources themselves, electrical sources themselves, they can be broadly classified as voltage source and current source. In the voltage sources, the voltage is determined by the source and it is held constant. In the current source, the current is determined by the source and it is held constant. Whereas the other parameter, like in the case of the voltage sources, the other parameter would be the current, which is determined by the external circuit. And in the case of the current sources, the other parameter, which is the voltage, is determined by the external circuit. The sources are further classified as AC sources, alternating current sources, or direct current sources. Likewise, even in the current, you have two classifications, the AC and the DC. Let us now look at how a voltage source and the current source is represented symbolically, and of course its ideal characteristics. So let us consider a voltage source. The voltage source is symbolically represented by a circular symbol with two terminal leads coming out of it. It has an arrow pointing, I will just come to that, pointing in a manner as shown here. This arrow indicates that this potential, this terminal potential is measured with respect to this. That is what this arrow indicates. Okay. And then there is a current going out of the one of the terminals, and then it circulates and enters the other terminal. This is the symbolic representation of a voltage source. It is also represented in a slightly modified manner in many of the literature. Voltage source, instead of the arrow, plus and minus mark are used. It does not indicate that this is always positive with respect to this, but what it indicates that measurement of this terminal voltage is done with respect to this. Okay. So this is the symbolic representation of a voltage source. How do we represent a current source? Current sources are also represented in a similar manner. You have a circular block with two terminals, and there is a arrow within the circular block which indicates the direction of the flow of the current, and an eye to indicate that it is a current source. Now this is the terminal, and the terminal voltage for the current source is determined by the external circuit. So this is one such representation of a current source. Alternatively, you can see a current source being represented in this manner also. A double circle with an arrow indicating the flow of direction of flow of current, and an eye to indicate that it is a current source, and the terminal voltage Vt, which is determined by the external circuit. Important characteristic of a source is its IV characteristic. IV characteristic gives a very nice description of the voltage source in a pictorial form. Now, if you take a voltage source, and look at its IV characteristic, So, let us draw the XY plot. The x axis is the load current I. The y axis is the voltage of the voltage source. Now, if we look at the plot of this, you will see that in the case of the voltage source, the voltage will be a constant with respect to the current I. So, whatever may be the current here, this current here is the load current. So, whatever may be the load current, the voltage will be a constant at some value, let us say V naught. Likewise, if you take the current source can also be represented by an IV characteristic. In the case of the IV characteristic of a current source, the independent variable is not current, but the terminal voltage Vt, and the dependent variable here on the y axis will be the source current. So, you will see that whatever may be the terminal voltage, which is the load for the current source, the current value will be a constant at some value, say I naught. So, in the case of the voltage source, the voltage is constant with respect to the load or the load current, and in the case of the current source, the current is constant with respect to its load, which is the terminal voltage, the terminal voltage being decided by the external circuit. These are ideal characteristics. Only in the ideal characteristics you will see the voltage source and the current source IV characteristic, where the waveform is a horizontal straight line. But in a practical characteristic, it is going to deviate from this horizontal straight line significantly, and later on we will see how these non-idealities are going to affect the IV characteristics of these sources. Before going into the non-ideal or the practical sources, let us have a look at how an AC source look like. The AC source or the alternating current source. In the case of a DC source, if we look at the waveform of, let us say, a voltage source with respect to time t, voltage with respect to time t, you will see that it is a constant. So, this is the waveform that you would see for a DC source. But if you take the case of an AC source, the AC source with respect to time t, the waveform need not be a constant, but it could be varying in some arbitrary fashion. Okay. So, this would be an AC source. This would be an AC source. So, an AC source, the voltage waveform or the current waveform of that particular source varies, goes positive and negative, or has a varying component as a function of time. Whereas, in the case of the DC source, as a function of time, the value of the voltage of the current is going to be constant. The most common AC source that you would probably have come across is the source that you would see, the waveform that you would see when measuring the voltage of a wall outlet. The wall outlet waveform typically is an alternating current waveform. Let me first draw the wave shape with respect to time. It is a sinusoidal waveform. And it has a repeating period t, which means this portion of the waveform keeps repeating every period of time t. Now this waveform, called the sinusoidal waveform, is characterized by a peak amplitude Vm, and this whole equation is given as Vm sine 2 pi by t, that is the period t, into the time. So this is the equation that defines this blue colored waveform which is here, and this is the type of waveform that you will see across every wall outlet, and majority of the cases the AC waveforms that you will come across will be of this sinusoidal nature. Now here, what is constant? When you say it is a voltage source, with respect to load, what is it that is constant independent of variation of the load? It is this Vm amplitude. So if we plot this Vm, with respect to the load I, and this is, let us say, Vm, the peak value, you will see that it will be constant. The peak value or the Vm of the sine wave is constant, whatever may be the value of the load current I. Okay. So in this case of the AC sources, we have to take one characteristic feature of the waveform, like the V peak or which is the Vm, or the average value or the RMS value, any one of these which will define that particular waveform, and that will be constant with respect to the load. So now we will discuss about some practical sources. What is it different in a practical sources as compared to the ideal source? So in the case of the practical source, there is a source, let us say a voltage source V, with this following representation that we already discussed, and to its two terminals is connected a component Rs called the source resistance, and now the load is, our external circuit is connected across this these two terminals, and this is the terminal voltage. Okay. In the case of the ideal source, this component was not there. Rs was equal to 0 in the case of an ideal source. But in the case of all real practical sources, Rs is a finite value, a non-zero value, and it has an effect on the Vi characteristic of the source. So now the Vi characteristic of the source has to be seen with respect to this point. So it should be Vt versus the current I which is flowing here. So now let us have a look at the Vi characteristic of some practical sources. So let me draw a small scale down circuit of a source here. Let us construct this source, which is comprising of an ideal source V with the non-ideality of series resistance Rs, and there is the terminal voltage resulting due to connection to the external circuit. Now there is going to be a current that flows in the circuit here. Due to the flow of this current here, there is going to be a drop here across this resistance, and that is going to be IRS. That is, current into Rs is the voltage drop across this. So if you look at this entire loop, you see that V is equal to I into Rs plus terminal voltage Vt as determined by the external circuit. So now we need to know what is Vt with respect to the load current. Vt is V, which is the source voltage of the ideal source, minus I into Rs. So this is the load current. And this is the terminal voltage. So let us have a look at this equation. Let us picturize it and see how the IV characteristic looks like. So let me put down that equation here. V terminal equals the ideal source voltage minus I into Rs. Remember that in the case of the ideal source, Rs is equal to 0 and this component is not there, and therefore terminal voltage is same as V. But in the practical sources, Rs is not equal to 0 and therefore this component comes into the picture. So let us now draw the IV characteristic of such a practical source. Now the x-axis is I, the load current, which is the independent variable. The y-axis is Vt. Now at 0 load, so by saying 0 load, it means I is 0, which means there is no current flowing through the output circuit. So according to the equation, we see that I is equal to 0, this portion is not there, so Vt terminal voltage is same as V. So the terminal voltage starts with V. And if it had been ideal, we would have seen that it would have kept going straight horizontal. However, it is not ideal, therefore it starts at this point, and then as the current increases, this negative component keeps increasing, that is I into R keeps increasing, and subtracts from the ideal component V. So this amount of voltage drop is due to I into Rs. So in all practical power supplies or all practical voltage sources, you will see that the IV characteristic, the terminal voltage is not going to be horizontal, but it will be slightly angled down by amount which is equal to I into Rs, where Rs is the source internal impedance which is in series, and this equivalent series source impedance is 0 in an ideal case. So therefore the goodness of a voltage source can be quantitatively measured by looking at the IV characteristic. The more horizontal the IV characteristic, the better the source. So which means the more horizontal it is, the IRS drop is small, and therefore RS is small, and therefore it's a better source compared to one which has a much higher droop. Likewise, even in the case of a current source, there is an unideality that has to be introduced for practical current sources. So a practical current source is composed of an ideal current source, this is the current I, and this is supposed to be connected to the external circuit which determines the terminal voltage. And in the case of the practical current source, there is one more component that we are going to add across the source, and that is called the shunt resistor or shunt. In an ideal source, R shunt will be infinite, will be very, very high. In the case of a practical current source, R shunt is not infinite, but a value which is finite, but maybe in mega ohms and such, in that order. So now, if you look at this circuit, though the current source I is flowing here, it is now splitting into two parts. One portion of the current will flow in here and another portion of the current flowing here. So if you say this current is I shunt, let us say, which flows through the shunt path, the shunt resistance path, and this current is the terminal current, where I equals I terminal current plus I shunt. So therefore, I equals IT plus V terminal by R shunt. or in other words, if we rearrange this, we obtain terminal current equals the actual ideal source current value minus terminal voltage by R shunt. So, this would be the practical current source equation. Now, the terminal current will be same as the ideal current source current if R shunt had been infinite. So, in an ideal current source, R shunt would be infinite, and therefore, this term would be 0 and IT would be same as I. However, in a practical case, R shunt is not infinite. There is some contribution of this as Vt increases from 0 to a higher value. Now, let us look at the IV characteristic of this practical current source. Let me put back the equation. IT equals the actual ideal current source value minus terminal voltage by R shunt value. So, let us draw the IV characteristic. The x-axis contains is the variable which is Vt or the terminal voltage. The y-axis is IT. And at 0, when Vt is 0 means this is short circuit. When Vt is 0, that is short circuit condition, this portion, that is Vt by R shunt, is 0 because Vt is 0. I terminal is same as I. So, it starts from some value I, and if it had been ideal, R shunt would be infinite, and therefore, this would have gone horizontal straight like that. However, R shunt is not infinite in a practical case, and therefore, we see that this will start drooping as Vt increases, and this droop amount is Vt by R shunt. And here again we can say that the goodness of the current source is seen from this graph here. If this red line matches with the blue line, then it is closest to the ideal power source. Or if the red line starts deviating more and more away from the blue line, then the current source becomes poorer and poorer because the R shunt value becomes lower and lower. So, this can be used as a guide for comparing two or more current sources. Now, let us see some real world voltage sources. The first voltage source that we will be looking at is the battery, which is one of the most popular and ubiquitous voltage source that you would have seen everywhere and used probably in many of the electronic equipments and gadgets. The battery is a DC voltage source, meaning the voltage is a constant independent of the load current, and also it is a constant with respect to time. A typical battery looks something like this. There are many types and versions of batteries. This is one such battery. It has two terminals, one marked positive, which is red in color, the other one marked negative. We will have a closer look at the battery shortly. Before that, we will try to understand how we represent the battery on paper, meaning its symbolic representation. A battery is represented on paper symbolically in this fashion. It has a series of long and short horizontal lines and two terminals here, which is the terminals to which the external circuit is connected. The long line is positive or the anode, the short line is the cathode or the negative terminal, and we represent the voltage value of the battery by VB. So this is the symbolic representation of a ideal battery. What goes inside a battery? It is a can, let us say. It contains two electrodes, a positive electrode called the anode, a positive electrode called the anode, and the negative electrode called the cathode, and it would have inside an electrolyte. It has a electrolyte. These are the three important components of the battery: the positive electrode or the anode, the negative electrode or the cathode, and the electrolyte. In the case of the most popular battery, which is the lead acid battery, which you would also have heard used in almost all the automobiles, the positive electrode is lead oxide, the negative electrode is lead, and the electrolyte is dilute sulfuric acid, or should I say H2SO4. This is the chemical symbolic name of sulfuric acid. So this comprises a typical lead acid battery. The electrons get generated from the cathode, flow on to the anode, and from here to the external conductor, to the external circuit, then back again to the cathode. And in the process, as far as the lead acid battery is concerned, water is generated and it dilutes the battery and the charge goes down. So repeatedly, as the charge goes down, you will have to recharge the battery again back to its original capacity, which means the concentration is brought back, and then again it is in the charged condition. Let us now take a look at the battery which you are seeing in the picture here. This is the lead acid battery that I have been describing. This is a sealed maintenance free lead acid battery. The electrolyte is in gel form. This is the positive terminal or the anode. This is the negative terminal or the cathode. Whenever you see a practical battery, there will be some nameplate readings which are of importance to you. You will see here something is written on the side. Two of the most important things that you will have to see in the case of the battery is the terminal voltage. You will see that it is 12 volts, that is across these terminals. You will get nominal, this is the nominal DC voltage that you would get across these two terminals. And next to it there is something else written called 7AH. It means 7 ampere hours, which means you could draw 7 amps for 1 hour, but in actual practice you can't do that, but that's what it would imply. Each battery has maximum discharge current capability. So for example, if this is C10 battery, let us say, then you can draw 7 by 10, that is 0.7 amps for 10 hours. So which means 7 ampere hours, something like that one. So these two numbers you will have to bear in mind while designing batteries and or choosing batteries. This 12 volt into 7 ampere hours turns out to be 84 watt hours. So 84 watt hours is the energy capacity of this battery. So now coming back to the screen here, though the ideal battery has a symbol which is like this, as I explained earlier, a practical battery will have one more component introduced in series, which is the series resistance or in this case let us call it as RB. This is VB, this is the positive terminal and the negative terminal, and this is VT, the terminal voltage. So you see that RB will have a finite value in all practical batteries. If the battery had been ideal, RB would have been 0, but it is not so, unfortunately. So you will have some value, and further in the case of the batteries, RB is not constant. RB is a function of state of charge of the battery, state of charge of battery. What this means is, if the battery is fully charged, RB is low. If the battery is fully discharged, RB is high. So therefore we cannot take RB as a constant value also, like in the case of some of the sources. So how does the IV characteristic for a battery, a practical battery such as this, look like? Let us now draw the IV characteristic of this practical battery that we have been talking about. A battery which is composed of an ideal voltage source, DC voltage source, in series with the series resistance RB. So the y axis is the terminal voltage, the x axis is the load current I, so this point is load current of 0 amps or open circuit. Now when there is no load, there is no IB/RB drop, and therefore the terminal voltage is same as the battery source voltage under ideal conditions, which is VB itself. And if there had not been IB, this battery terminal voltage would have gone horizontal as shown here. However, due to the presence of RB, as the load current increases, there is going to be an IB/RB drop, which will make the terminal voltage to droop as shown here, and this droop is nothing but IB into RB. So if RB is less, then such a battery is fully charged or it's a good battery. If RB is high, then such a battery is either fully discharged or in poor condition. You should know that the battery IV characteristics that we just saw is more of a general nature. The exact IV characteristic will differ from battery to battery, from the type of the battery to type of the battery, from manufacturer to manufacturer, from ampere rating to ampere rating, and so on and so forth. So you should actually take the IV characteristic data from the manufacturer's data sheet for much more specific details. Now we shall go into another type of source called the solar photovoltaic cells. The solar photovoltaic cells. As the name suggests here, photovoltaic, the source is based on the principles of photoelectricity, which basically means that there is a p-n junction, an n-type material on a p-type substrate. So when sunlight falls on such a material, the valence electrons are excited and they move into the conduction band, and these conduction band electrons move in the external circuit and complete the circuit, and if there is a load like a light or a lamp, that will get lighted up. This is the principle of the photovoltaic cell, the most basic or simple in its most simplistic form. How do we represent the photovoltaic cell on paper? It is like this. We have a rectangular block like this and a small triangular niche there up. Looks like a post cover, and it has two terminals. So this terminal is the positive end and this terminal is the negative end. Okay. And we get the terminal voltage across these terminals. Okay. So this is the symbolic representation of a photovoltaic cell. Now we will see how a real world photovoltaic cell looks like. Typically photovoltaic cell looks something like this. This is one such photovoltaic cell, which is a polycrystalline cell. The one alongside is a monocrystalline cell. Let us have a closer look at this photovoltaic cell. You see, this is actually a p-n junction. The top layer would be an n-type layer, and the sun rays will fall on this, and on this there is the metallizations which are soldered on it on one layer, and on the back side also you will see the metallization, so that we can solder one lead on this and one lead on this side and take it off, and that would be the two layers of the photovoltaic cell. Typically the efficiency of this cell would be around 10 to 12%, which means if you have 1 kilowatt of energy falling on this, the terminal power that you would get, the electric power that you would get out of this cell would be something like 120 watts. Okay. So that is that's what an efficiency order of efficiency would be for any typical photovoltaic cell. Now coming back to the slide, general sources were categorized into two types. One is the voltage source and the other is the current source. However, the photovoltaic cell doesn't fall into either. In fact, it falls into both of these categories. It is a combination of both voltage source and the current source. This is a unique feature of the photovoltaic cell, which is special to these type of sources. So how does it behave? Both like a voltage source and also like a current source. So internally, if we look at the photovoltaic cell, its equivalent circuit, it consists of a current source. So I am drawing an ideal current source which is like this. this is shorted by a diode, bypassed by a diode like this, and the terminals of this go on towards the output terminals, and they result in the terminal voltage. Now, to this there are two components or non-idealities which get added. One is the shunt resistor, which is the non-ideality of the current source, and there is a series resistance which is the non-ideality of a voltage source. So, you see there is a current source, there is a non-ideality of the current source which is the shunt resistance, the non-ideality of the voltage source which is the series resistance, and then the terminal voltage Vt coming out there. So, these are the equivalent circuit of a typical solar cell would look like. Then what is the Vi characteristic of such a cell or such a source? Okay. So, let us have a look at the Vi characteristic of such a source. Let us first draw the axis. Y axis represent the current I, or the terminal current of the photovoltaic cell. Now, I told you just now that the photovoltaic cell or the solar cell behaves both as a current source and a voltage source. So, which means a current source implies that I should have a horizontal line like that. A voltage source implies that I should have a vertical line, something like that. So, a photovoltaic cell, an ideal photovoltaic cell will fall within this square template that I have right now drawn here. But there are some non-idealities in the solar cell, that is, it also has shunt resistance which is finite, it has a series resistance which is also finite, non-zero. The series resistance we know affects the voltage source parameter. So, instead of being vertical like that, the voltage source is going to deviate from the vertical because of the series resistance, or should I say the IRS drop. The shunt resistance is going to affect the current source parameter. So, because of the shunt resistance, it is going to deviate from the horizontal current source effect due to the non-idealities of the R shunt, and that is V by R shunt, where V shunt is the voltage across the R shunt. So, to that effect, to that amount, that much current keeps decreasing. So, a typical real world practical solar cell will have an IV characteristic as shown here in the red line. An ideal solar cell will have a characteristic as shown by the blue squarish or rectangleish pattern there. There are two critical points that you have to note in the case of the solar cell. One is this point and another is this point. This is called the short circuit current ISC point, and this is called open circuit voltage VOC point. In fact, these two parameters of the solar cell are data sheet parameters where you may have to choose when you want to choose the solar cell for design. Another point that is of interest also is an operating point around here, around the knee, which will give you the peak power. Peak power. This also is a data sheet point. Okay. Now, summarizing for now, we saw that electrical sources are of two categories, the voltage source and current source. The voltage source has a non-ideality, which is the series resistance Rs, because of which the voltage is not going to be truly horizontal but drooping. The current source is having a non-ideality R shunt. R shunt is supposed to be infinite in the ideal case, but it is some large finite value in the practical case. And then we saw few real world sources, that is the battery and the solar cell. You should keep in mind that the internal resistance Rs and the R shunt that we have seen in the discussion of today need not be purely resistive. It could also be inductive, or it could also be a combination of resistive, inductive and capacitive. That is, it could be an equivalent series impedance instead of just equivalent series resistance in the case of the voltage source, or an equivalent shunt impedance instead of a simple equivalent shunt resistance in the case of the current sources. And of course, we did have a close look at these sources here, the lead acid battery and the polycrystalline, the monocrystalline solar cells. These two sources are DC voltage sources, DC voltage and current sources in the case of solar cell, a DC voltage source in the case of the battery. In the next class, we will see the characteristics of the AC source, one of the most important sources, which is the wall outlet, which comes from the wall outlet, which is the 230 volt mains.